even seen this. I'm really excited about Tealish. And we've got the CTO from Tinyman, Fergal Walsh, going to join us here today to introduce what is Tealish, a new higher level language for TEAL. So take it away. Welcome.
Hello, everybody. Hi. So, as Ryan said, I'm Fergal Walsh. I'm CTO of Tinyman. So, as you may know, just last week we announced Tinyman AMM version 2. So, or for those of you who don't know anything about Tinyman, Tinyman is the original decentralized exchange in Algorand. We've been around for about a year on mainnet. So V2 was announced last week, and it's going to be, the contracts are public. The audit reports and the protocol details are now public. It's going to be deployed to mainnet in January 23. These new contracts, we're pretty excited about them. They contain nice new features like flexible liquidity, flash loans, flash swaps, but most importantly, they're composable and interoperable with other protocols on the Algorand network. So we take advantage of all of the new great features available in the AVM that have been developed over the last year and rebuild the contracts from ground up. But I'm not here to talk about Tinyman AMM today, or really anything to do with Tinyman at all. I'm talking about something called Tealish. So in order to build Tinyman V2, we first built this thing called Tealish. So Tealish, the tagline is a readable language for Algorand. So it's a new smart contract language for Algorand, but maybe not a language, maybe a dialect of TEAL for Algorand. So in this talk, I'm going to talk about why we built it, about how we built it, and why that might be of interest to you. This is not an introduction to Tealish, so I'm not going to walk through how to build a contract in Tealish, but more the design, the design of the language itself. So why did we build a new language for Algorand? Well, Algorand has a bit of a problem. I'm sorry to say that so bluntly, but at the moment, it does. The developer experience is just it's not good enough. It's okay, but it's not good enough. It's holding us back as an ecosystem because the tools are still quite a struggle to work with. Now, we're still quite early. We're only a few years into this project. We're thinking very, very long term with Algorand, but we need to accept that it is a problem at the moment, and then see what we can do about it. So I didn't always think this way. I thought that Algorand had fantastic tools. I loved the language of TEAL. We at Tinyman loved it. We loved TEAL in the same way that we loved Algorand itself. We loved the elegance of it, the simplicity of it. It's brutal, but it's kind of beautiful in the same way. It's very low level, but there's no abstractions that get in the way of writing programs. It's very easy to understand what's going on. You're programming directly for the AVM, and that's very, very powerful. And obviously, it's very fast. The AVM is extremely optimized, and it felt pretty safe for working in. And so we wrote our Tinyman V1 in TEAL, TEAL version 4, actually mostly TEAL version 3, just a few things from 4 towards the end. But when we reflected about the experience of writing Tinyman V1, we realized it was a pretty inefficient process. It was inefficient, it was stressful, it was exhausting. We put in huge amount of efforts and endured a lot of stress to write something that is actually very, very simple. Like the maths and logic of an AMM, a basic AMM, of what Tinyman was, is very, very simple. But it took an extreme amount of effort to get there. And by any reasonable standards, our code is not readable. Like, we put a lot of effort into writing our TEAL in a readable way. We put a lot of effort into commenting it. But is this really the way to build the future of finance? Is this how we should be writing contracts for the future of finance in 2022? Like, when we tried to think about Tinyman version 2, we just couldn't fathom how we would build the things where we knew we could build them with the AVM features. We knew what we wanted to build, but we couldn't think how we were going to manage to build a program of that size with the current tools. So what actually is the problem? Like, why do I say that's unreadable? Why was it so stressful and exhausting to write that kind of code? So Tealish is kind of, as I said, it's fun, it's awesome to write small little programs. It's great while you're in the zone. But TEAL relies too much on our poor brains. Too much burden is placed on the writer of the code. And our brains are pretty limited. They don't have a very big stack. Our slot spaces are very low. So mental stack overflows became a real thing. As you try to write TEAL code and as you read TEAL code, and I'll get into this more and more, but reading is so important for smart contracts. People need to be able to read the code. And so you spend a lot of time trying to load up the whole code into the stack on your head, understanding what's going on. The slightest interruption, and you lose an hour of work. You have to start again, and it's insane. So this is not actually an efficient way to write big programs. It's great for small stuff. It's fun. It's really great solving challenges in TEAL, but it's not an efficient way to write serious programs. So, I mean, Tealish, okay, I keep doing that. TEAL is kind of what we see on the left here. It kind of goes top to bottom, but our minds don't work like that. We are conditioned to read programs from left to right. We like to have kind of expressions inside each other. We like to have stuff in one line. We're pretty good at reading programs like that. TEAL doesn't have common abstractions, so yes, you can do conditional stuff, you can do if this, else that, blah, but it involves a lot of manual work, it involves a lot of lines of code to do quite simple branching and things. There's a lot of burden placed on the developer. So does it have to be this hard? Well, okay. So at this point, probably about half of you are politely in your head, but you're still screaming at me saying, what about PyTEAL? Why aren't you using PyTEAL? Surely it solves the problems. And, okay, PyTEAL, it is great. It is a great effort at improving the way of making TEAL programs more readable. But it's just weird. As an experienced Python programmer, it is extremely confusing. If you're experienced in TEAL and Python, it's doubly confusing because you're trying to keep in mind the differences between Python and TEAL, or Python and PyTEAL. You're trying to figure out which, like, I know how to do an if statement in Python, but that's not how I do it in TEAL. But I will do a normal Python if statement inside of my PyTEAL code, but that bit is for generating actually an AST, not the runtime code. It's really confusing. I've used PyTEAL quite a bit. I try to explain it to my colleagues, and I just get so confused, and I find it a struggle to explain. And then as I try to debug contracts that I've written in PyTEAL, I keep finding I have to go back to the TEAL. And then there isn't a one-to-one mapping, and it's just quite difficult. Now, I know Beaker is doing a lot to improve this and adding a lot of structure to that, and that's a really great improvement. But in the end, it's still PyTEAL in there. And the guts of the programs are still PyTEAL, and they're the bits where the important stuff happens. So we wanted something better. And I mean, we don't want to fragment the ecosystem into multiple languages. But at the same time, I really believe it's too early to settle for mediocre tools. So, as I said, we're only a few years into this, in this Algorand ecosystem. If we're going to be in this for long term, we need good tools, and we shouldn't try to just settle too early on the first thing that we try. So, I really believe we need to try multiple things and see what works, see what doesn't. I don't believe Tealish is going to be the future of Algorand. There may be many things that will come later and can replace it or do things much better than anything that we can think of, but we want to offer an alternative to the tools that are there at the moment, an alternative way of thinking about the problem. So what do we want? We want an AVM native language. It is a unique virtual machine. We want a language that works for that. But we want a language that is designed for the AVM and humans. Humans are a hugely important part of the process of reading and writing contracts, much more so than normal software development. We want a language where intent is obvious and semantic mistakes can easily be found. We want a language where we can iterate on ideas, where we're not afraid to write some code, try it out, throw it away, rewrite it, and keep ideating and iterating until it's as good as we can get it. We want a language that's easy to debug. We want a language that generates auditable code. Now, this is really weird. Like most programming languages, they develop bytecode, and you don't care what the bytecode does as long as it works. We want to generate auditable TEAL. TEAL is the output of Tealish, and we want that TEAL to be readable and auditable by professional auditors or by independent, knowledgeable people who know about TEAL, so that they don't need to trust the Tealish compiler. The Tealish compiler will be continuously developed, but they should, if they have good knowledge of TEAL, they should be able to understand the TEAL and ensure that it does what it's meant to do or what they think it does. We want a language that our technical users can understand by reading our contracts. Basically, we want a readable language for Algorand. Now, when I say readable, like readability is in the eye of the beholder. So who are we talking about for readability? It's the developers, it's the auditors, it's the reviewers, so your teammates reviewing your code, and it's the technical users of this ecosystem. If we're writing a protocol, those users should be able to read our contracts and understand exactly what we're doing. So what is readable? To me, readability means this. It's a familiar syntax, so when you look at the code, it should not be insane. It should look like other programming languages to some extent. There should be a good balance between verbosity and terseness. It should be explicit, so there shouldn't be magical things happening. It should be predictable. You should have a good idea of what's going to happen when this code gets executed or this code gets compiled. It should be strict. So I love Python. When I'm not doing TEAL or Tealish, I'm doing Python. Python is not strict, and I love that fact about it. But I don't use Python for writing smart contracts. I want my smart contract language to be extremely strict. I don't want it to be generous or forgiving while it's compiling. I want it to be strict about types. I want to be strict about exactly how I use it. I want a consistent style. So there should be one way to write this language. You shouldn't be able to have a choice. You shouldn't be able to decide where you put your brackets, how you format your code. That's not important, and it doesn't add to readability. There should be an abstraction of common patterns. It makes it easier to recode. If statements look like if statements, you know how they work. You can look at the details. You don't need to look at the structure of it. There should be compartmentalized code. So you should have some way of scoping your code so that you can look at bits of code, chunks of code, bit by bit, and understand them in isolation. So with this aim in mind, we started building TEAL. So we thought of our favorite language as this, and we decided to mix them together. So we basically took Haskell, Perl, and that's definitely not what we did. We started with TEAL, and we said, what do we need to add to TEAL what do we need to mix with TEAL to make it into a readable language? So we're working up from TEAL. And why are we working up from TEAL? Because, as I said, we want something that is for the AVM. So the TEAL is designed for the AVM. TEAL has all the opcodes are very, very specific to how the AVM works. And we want learning our language to equate to understanding the AVM. So we don't want to re-implement stuff that's in the AVM. We don't want to implement it in different ways. We just want, if you learn Tealish, if you understand Tealish, you understand the AVM, and vice versa. So first and foremost, we want to make the stack implicit. So instead of putting stuff vertically in your program, let's just put it horizontally. Infix notation is easier to read for most people than prefix. And then we want some kind of expressions. So we put those expressions inside functions. So if we're using the assert opcode, an opcode is like a function. It takes some arguments. So those arguments, we put them we can use expressions as arguments. So we write this like this. By the way, the first line is not valid Tealish. It's an expression, but it's not a statement. So that you can't use 2 + 1 is nothing. Where does the result go? What are you doing with it? So the second line is the first piece of valid Tealish. Then we can have more complicated expressions, and then we can use other opcodes in our expression. So if an opcode has a return value, then we use that as an expression. And we just use the opcode directly. So apt global get, if you look that up in the opcodes document on the Algorand developer portal, that's exactly what it says. app_global_get. That's the name of the opcode. And then this is the first time we see something that we say, well, maybe we can make this a little bit nicer. Maybe, okay, you got a magic number there. Let's extract that out. That's a constant. Let's give it a name. So we just tell the compiler that this thing has a name. We give it a type so that we can do type checking later. And then here we see another opportunity for making it easier to read. So we could just kind of stay pure and say, well, there's this global opcode, and it has this, the first argument is the name of a field, so we just pass it as an argument to the function. But it would be maybe more readable, more understandable to use a namespace and field kind of syntax. So we have global.round and txn.applicationargs. And applicationargs is an array, so it makes you can index into that array, and it just uses standard other language in the world. Okay, so now we move on to slots. So in our TEAL programs, we want to temporarily store stuff into slots. Unless you're JJ, you need to use slots. JJ can do everything on the stack, but normal people need to use slots to temporarily store pieces of information. So normally you just put these into, you number your slots, and in the Tinyman version 1, we kind of came up with a scheme for trying to remember the slot numbers for each thing. So if it was a number ending in 1, it referred to something to do with asset 1, and if it ended in 2, it was asset 2. And then there was other magic numbers like 42 and 57 and things, but we tried to keep some kind of sensible structure to it because we had no other way of keeping track. We were trying to keep track ourselves. But why not just use names? So we use slots like variables. So we have a pool address. So we define bytes, pool address equals transaction accounts 1. We use typing, as I said earlier. It's more friction for the developer, but there's lots of advantages just to having types. Okay, so at this point I'm going to flip things around and show, okay, we have our Tealish. So what does our Tealish do when we compile it? Well, our Tealish kind of turns back into what was on the other side of the slides. It turns back into TEAL. But it's not just, and it is TEAL, it's not the bytecode, it's actual TEAL text. And why is it TEAL text? Because it has all of these comments and annotations. So each line of the generated TEAL includes the original line of Tealish as a comment to explain the intent of what's happening. Every time they use a slot, it includes the Tealish line, and then includes the variable name as a comment on the TEAL lines. And it also includes the original developer comments. So then as you read through the generated TEAL, you have the full context of what the developer was thinking as they were writing the code. And all of this is generated by the compiler, so you know that every single time that a slot is accessed, there is going to be a comment to tell you what that slot was for. So once you have slots, then, well, we have 256 slots, which seems like a lot, but then when you try to do a lot of stuff in a contract, you're going to run out of slots. So we need some way of scoping so that we can tell the compiler that, okay, we're using these slots at the moment, but after this point, we no longer care about those slots. They're out of scope. We're not going to read from them again, so you can reuse them. So we introduced this concept of the block, a block of code, and they're named, and you basically jump between blocks of code. This is very similar to how people write TEAL code. They have labels, and then they do things within those blocks of TEAL code, analogous to that. And so we define our variables inside our blocks. Tealish automatically assigns the slot numbers, and then once it goes out of scope, those slots can be reused. And then a common pattern is jumping between different sections of code. Usually this happens at the start. Sometimes it happens you do some kind of conditional stuff at the start, you jump into a main method, and then you do some other conditions, and you jump to further sub kind of stuff. So this switch statement is basically just taking this very common pattern and turning it into something a bit more readable, less boilerplate code. It looks like we could make this even more magical, and you just pass in the method names and it would automatically jump to the functions, but we're trying to avoid any kind of magic to make it more obvious what the language is doing. Okay, the next most common type of thing that you're going to do in a TEAL program is some kind of conditional stuff. So if this, then we're going to do that, otherwise we're going to do something else. But all with it just like in close proximity to each other. So this very common pattern, we just turn it into a if statement. And this is really boring. Like, this looks kind of like an if statement, and there's elifs and elses, and it's exactly like in other languages. And it's meant to be boring. Like, there's nothing interesting about this. It shouldn't be exciting. It should just be really boring and really predictable about what it does. And now that we've put it into this form, then actually maybe it's easier to notice some possible logic errors that are in your code, which are less easy to spot when it's written in the Tealish style, in the original TEAL style. Okay, inner transactions. So these are one of the unique features of the AVM. Every modern application on Algorand uses inner transactions. They're a core building block of protocols. So we wanted to give them first-class treatment in Tealish. So in TEAL, they look like this. You begin a transaction, and then you have some fields, and then you put some stuff onto the stack, and you store them into those fields. So in Tealish, we just basically remove the excess stuff and just turn it down into its most simplest form without losing any information. So you have your inner transaction, you have your fields, and you put your values in those fields. And then you have groups. We have, like, inner transactions can be in groups, so we have just a group concept here. And by the way, like, in my examples, I'm showing them nicely formatted and stuff. You can write your Tealish like this, and it's not going to be so readable. But the compiler will just put it back into the right way to write Tealish. So then your colleagues will be able to read your code. Or if your colleague doesn't write the code properly, you just automatically fix it. So that's the Tealish. Fixes it for you. So then we have functions. So in the AVM, there's a support for subroutines with call sub and ret sub. And so these are functions, basically. So in Tealish, we have a kind of a fairly standard syntax for functions. Again, we have types, so types are tracked everywhere throughout the program. At the moment, and then our calling style for functions is exactly like opcode, so we're just passing in arguments, and those arguments can be literals or expressions. At the moment, our functions look exactly like this, so the arguments that you pass in, they get stored into slots, and then we do stuff with them. In AVM8, this is all changing with frame pointers. I have finally understood frame pointers in the last 2 days, and they're going to be awesome. They remove a lot of the challenges that we have with functions at the moment. And so instead of storing stuff into slots, we'll be using frame pointers to reference variables, and that's going to allow for much more scalable programs. Right now, we try to keep functions as small as possible, limited in what they do, limiting the amount of space, amount of local variables that they have. With frame pointers, that's not going to be an issue anymore. Some stuff, we just kind of left it as it is. So this is some maths. This is extract from Tinyman v2. And it looks kind of ugly. That's not beautiful. But if you take the time to read it, it's unambiguous. There is no two ways of understanding what it does. If you read it, you understand exactly what the compiler and what the AVM is going to do with those, with that information and the mathematical operations it's going to do. Like you have this ugly operator B star, and then you have B slash for divide, and then you have normal pluses. You might have some B pluses in here, but they're important. They're really important. When you use a B star versus a star, that needs to be explicit in your program because they mean totally different things, and they have totally different costs. So it's important to be explicit about when you're using them and make sure you're using them in the right places, but not overusing them. So we just left this as it is. If we attempted to make it more beautiful, we might have just make it less readable, actually. So these are all the features that we needed to write AMM v2. So infix math and logic operators, expressions, where we have expressions inside expressions, calling opcodes, some constants, accessing fields like globals and transaction and gtransaction and all those things, variables, scopes, conditionals, inner transactions, and functions. Well, not quite. There was some other stuff we needed. We needed this. So I make typos and spelling mistakes all the time. We needed our compiler to understand when we make mistakes in our code. So that has not been defined, or you spell the variable wrong, or all these kind of things, you get a compiler error, as you would expect. We're trying to assign the results of this multiplication into an integer variable, but actually, that's not an integer, that's still a byte. So it's telling you that you're doing the wrong thing. And here, it's telling us that we have one name, but there's two values. So asset params get returns two things, so you need to consume them. You need to do something with both of the return values from that opcode. And then we needed lots of these. So we had tests where our tests ensure that a specific line of Tealish with an assertion is being raised in certain scenarios. So our tests are written using another tool called Algorand, which we also developed in tandem with this. That's a whole topic for another day, but basically it allows us to test against a very specific known state of the ledger, and then to assert that certain things have happened properly or that the correct assertions have been raised. Now, all of these things are possible, like those proper error messages, these asserting that a specific line of Tealish has caused the error. These are possible because this is a parsed language with a language model and a source map. So we know exactly when we get a PC counter error from the algod, we know we can map that back to the TEAL and back to the Tealish, so we would know which line and which characters on that line caused the error. So developer experience tooling was super important. So with these features, we gain new contract writing abilities, basically. We are able to ideate and iterate on the code. We were able to keep changing as we went along and to work to build really exactly what we wanted to do. We did, like, once we had built something, we didn't get stuck on it because it was easy to change. It was easy to keep on iterating and refactoring until we had it exactly as we wanted. And it was easy to quickly notice mistakes. Sorry. Seems like this thing's powered by the blockchain or something. So in Tinyman v2, we had over 1,000 lines of Tealish, 15 or so distinct methods, a lot of maths, and it's a fully composable, flexible protocol, and we have a lot of safety checks in there. And this results in over 3,500 lines of TEAL. That's commented, annotated TEAL. And so this generated TEAL, it's pretty readable because it has all of those comments in it. It has our intent it has comments for all the variables that we're using. And so I should mention that these contracts have been audited at multiple levels. So they've been audited at our business logic. They've been audited at the TEALish level. So the auditors have basically generated models and done analysis based on the business logic that we've described in TEALish. And then it has been audited at the TEAL level. So they've read through all 3,700 lines of this TEAL to ensure that it maps to our business logic. So they're not relying on, and we are not relying on the accuracy of our compiler. It's still audited in the exact same way that any Algorand smart contract should be, which is the actual code that gets executed by the AVM. And the auditors had great comments about, so they didn't balk at the idea of auditing contracts written in a new language. They were quite happy to audit the TEALish, and they had very positive comments about the readability and usability of it. So that told us that it worked. We achieved the aim of creating a readable contract. So this is what we needed for our AMM v2. So what's next? Where does it end? Well, probably we'd want to do stuff like loops and structs and arrays and classes and interfaces and inheritance and polymorphism and all the other stuff. Or would we? Is that really what we want? Do we want feature parity with Python or Go or other general purpose programming languages? Well, to answer those, we should go back to our design assumptions of what we were thinking of when we designed this language. And our assumptions are that program size for contracts will always be small. So the size of programs is not going to scale with Moore's law. There's a totally different rules of scaling that apply on the blockchain where you have thousands of transactions that need to be executed in seconds. The runtime memory constraints are always going to be small. So cost optimization is always going to be important. And we assume that the AVM capabilities will always be limited and very domain specific. Algorand does not try to be the world computer. It has a very specific domain, and the AVM has very, very specific opcodes. It has a specific use case. So in our view, most of those possible features and features of other languages just are not appropriate for contracts on Algorand. We don't need them, probably. There are some stuff that we do need for sure, like loops and structs and arrays and more. But we want to keep it simple. We want to keep it so TEALish is easily digestible. We want to add this little extra burden to the developer. So we want knowledge of TEALish to equate to knowledge of the AVM, and vice versa. So we don't want loads of extra stuff at the TEALish level that is unique to TEALish. We don't ever want to see this article about the 10 things you didn't know about TEALish. There should be nothing you don't know about TEALish after you've read the documentation, which is not very long. We want it to be very easy for people to keep in their head. But we do need stuff like loops and things that are fairly standard. We didn't need them in Tinyman AMM2, but we always had them in mind as a feature. So we have while loops and we have for loops, and they're boring. They just kind of do what you would expect them to do. And the TEAL they generate is really boring. We have structs. These are interesting. These are nice. So one common pattern that we've seen is people putting loads of stuff into byte strings and then putting those into global states or local states, or now with boxes. And there's a very good use case for this. But it's really painful to manually manage the offsets and the sizes of your types and all these kind of things. So we thought, why not just define in the language a way of defining your data structure? So we can say that we have some ints and we have some bytes, and they have an order in these byte strings. But all of this happens at the compiler level. So this is managed by the compiler, not by the AVM, not by runtime code. So the code that is generated is exactly the same as what a human would generate with the same problem, just the human didn't need to think about it at that level. So these are already in TEALish. Arrays are coming soon. They will follow the exact same way that structs work for static types, not for dynamic types. So we don't expect to add like dynamic length strings anytime soon, or dynamic length arrays. because that involves runtime computation in the AVM. It gets a lot more complicated and it's a lot harder to reason about, and I really want to be sure that it's necessary to have that before we implement it. So how is Tealish going to keep up to date with the AVM? What about, like, let's imagine a few weeks ago you wanted to play with boxes. You heard boxes were coming. You saw the PRs on Go Algorand, and you're really excited to try them out. So you write some code. You know how to use it. Like Tealish, you don't know how to use boxes in Tealish because you don't need to know how to use boxes in Tealish. You know the opcodes, so you know how to write it in Tealish. So you write some code, and then you go to compile it, and then, unknown function or opcode box create. Okay. You check up the documentation, you make sure that it wasn't create box. No, it's really box create. Okay, I spelled it right. What's going on? So you search the repo, and okay, Tealish hasn't implemented boxes. What am I going to do? I can't use Tealish. Okay, I'll go back to TEAL and I'll try to, no, you don't. I'll search like for app local get. That's an old opcode. I know it exists. I'm going to check how that's implemented in Tealish. And it's not. It's just there in a JSON file. That's not an implementation. We were lying to you. We didn't implement any of this stuff. So what's going on? That JSON file is, well, that's the specification of all of the opcodes that exist in Algorand. And that's how Tealish knows about opcodes. So Tealish has no implementation for the vast majority of opcodes because it doesn't need to, because this file tells Tealish how it works. So Tealish has a CLI, and in that CLI, there's some line spec tools. And those tools allow you to fetch a new version of the line spec. So you heard about boxes, you saw that it's been developed on a feature branch, and you say, I want to use that with Tealish. So you go Tealish line spec fetch feature AVM box. So feature AVM box is the name of the branch on Go Algorand. So you're fetching the line spec file from there, and you get the new opcodes. And then you can try to compile your code again, and it tells you that you actually used that box create opcode wrong. It was expecting 2 arguments. You fix that, and then you have compiled your code. And now you can actually experiment with those features in Tealish directly, even though Tealish didn't know anything about those opcodes. So this is how Tealish is going to support the AVM going forward. There does not need to be any special work done on Tealish to support AVM 9, 10, 11, 12 for the new opcodes. But sometimes we might want to add syntactic sugar. So like, for example, this boxes example, we thought of, well, okay, boxes they're nice and simple, but they get complicated. There's box extract, box replace. You need to use these sometimes. And that's kind of like extract and replace that we have for working with byte strings. So maybe we can support them in the same way. So we introduce a box type in Tealish, and then we have this kind of generics type of syntax where you say, I'm creating a box, and it has a type which is defined by a struct. So this is a box that contains this kind of structured data. And now when I read and write to that box, I use the fields of the box, and internally that uses box replace and box extract as it needs to do. And so that can work for as large boxes as are possible on the AVM. So that's some syntactic sugar that is added on top of the opcodes. That's an example there, don't need to go into that. Okay, so on our roadmap, we're continuing to develop it. There's still some further work needed, some other things we would like to add, like the arrays example that I mentioned. We also want to add some support for external functions. So I mentioned that functions are getting a revamp, and finally, we have a nice way to support functions of reasonable size without awkward restrictions. So then we're going to be able to support declaration of functions to mark them as external, and then have ABI router type of support in Tealish. Developer tools will continue to improve. The compiler can get better and better. It can give you better and better error messages. We're working on a debugger or replayer for in conjunction with our testing toolkit, so that we can make it easier to debug contracts. And we also have test coverage tools, so that basically for all of our tests, we can ensure that When we run our tests, we keep all the traces, and then we ensure that every single line of Tealish has been executed by our tests, which is really nice to have. And then, because we have a language model, we can implement static analyzers, which can automatically check for common types of issues in contracts. And then continuous documentation improvements. And then, so on most language roadmaps, one of the items on the roadmap is the Tealish compiler in Tealish, or X compiler in X. We never want to see this. If this is possible, it means the project has failed. And there's one guy right there who I know is going to try to do it. But hopefully it should be impossible. That is not an aim of the project. This is a very domain-specific language. So one of the things we like about Python is the Zen of Python. In the Zen of Python, the developers have basically written down some things which capture their vision and design philosophy for the language. When we talk with developers in our company, and especially for newcomers to the language, we often refer to the Zen of Python. We often say, like, the Zen of Python says explicit is better than implicit. So in your code, you should be explicit. We refer back to other things. So we came up with a Zen of Tealish. We borrowed directly explicit is better than implicit, because especially for contracts, it really is. But there's also a bunch of other things that we think are really important. I won't go through them all, but code is both for humans and machines. Readability is more important than writability. They are the main 2 points of our design philosophy, and that's what led us to building Tealish the way it is. So if you'd like to learn more about the project, we have a read the docs, so tealish.readthedocs.io. We have a GitHub, and you can obviously learn more about us at tinyman.org. Thank you.
Fergal, awesome talk. Honest criticism to bring us in about, how do we reason about TEAL? Tealish is definitely something that we are all very interested in. If I ask this question, are there questions out there? This whole room is going to have every single hand up. You will be here until all night long. So I'm not going to do that, but I am going to invite all of you to